How do control loops work in robotics? Imagine trying to keep a ball steady on your hand without dropping it. That's similar to how control loops help robots stay on track and perform tasks accurately. Control loops in robotics are systems that constantly watch what a robot is doing and make adjustments so it stays on course. They do this by comparing what the robot is doing now with what it should be doing, which is called the set point. The difference between these two is called the error. The system then uses this error to decide how to fix the problem. At the heart of a control loop are three main parts: a sensor, a controller, and an actuator. The sensor measures a physical thing like position, speed, or angle. The controller takes this measurement and compares it to the set point, calculating the error. Based on that error, the controller sends a signal to the actuator, which is the part that moves or adjusts the robot. The actuator then makes the necessary change to bring the robot closer to the desired state. Most control loops in robotics are closed loops, meaning they use feedback from sensors to keep adjusting. This is different from open-loop systems that don't check the output after making adjustments. Closed-loop systems are better for robotics because they respond to changes and disturbances, like a gust of wind or uneven terrain. One common type of control loop is called a PID controller. PID stands for proportional integral derivative. The proportional part reacts to the current error, giving a quick response. The integral part looks at the sum of past errors to fix any steady mistakes. The derivative part predicts future errors based on how fast the error is changing, helping to prevent overshooting the target. In robot programming, PID controllers are used a lot. They help control motors, robotic arms, and other parts to move precisely. For example, a robotic arm can use a PID loop to reach a specific position without overshooting or shaking. Control loops can be layered. An inner loop might control how fast a robot spins or moves, running very quickly to keep stability. An outer loop then manages the overall position or speed, relying on the inner loop to keep things steady. In practical terms, when you program a robot, you set up these control loops so the robot can move smoothly and accurately. The software constantly checks the current state, compares it to the goal, and adjusts motor power to keep everything on track. This prevents the robot from overshooting its target and reduces stress on the mechanical parts, helping them last longer. Many advanced motor controllers have built-in control loops that run very fast, sometimes every 1,000th of a second. This makes the robot more responsive and precise without overloading the main processor. Some controllers even add extra features called feed-forward terms, which help predict how the system will behave and improve control even more. In short, control loops are the backbone of robotics. They let robots perform tasks accurately and reliably by constantly sensing, comparing, and adjusting their actions in real time. Learning how to write these algorithms is key to making robots that move smoothly and work well in complex situations.